Welcome to this video. We are going to learn about standing waves. First, there's this thing called a standing wave, and it's different from a traveling wave, or what we call a progressive wave. So over on the right, I'm going to show you what a progressive wave looks like. There are some waves that look like this. On the left, we will show a standing wave, which is quite different. Here's the progressive wave. You see crests moving along to the right, and here's the standing wave. The crests are not moving, they're staying in the same spot. Here the crests move, and on the left they don't. Let's record this in the notes. First, in the notes, scratch out Unit 7. This is still Topic 4. A standing wave, that's the question. What does it look like? Well, we'll start out by first drawing a progressive or a traveling wave. That's one where the crests and troughs move forward as time passes. So here they are after a little while, and then after some more time has passed, they look like this. So there is forward motion of the wave shape, which we also call a profile. The profile or the shape moves forward, and it progresses through the medium. A standing wave, on the other hand, is very different. A standing wave starts out with something like this, maybe, and then after a little bit of time, right? After a little bit of time, it looks like this. When some time has passed. Oops, that's not so good. Let me try again. And then after a little more time has passed, it's like a flat line. And then after more time has passed, it's like this. And then after a little more time has passed, it goes to here. And it's each point on the string is just going up and down, but the crests stay in the same spot. The location of crests, troughs, or compressions, rarefactions stays the same. Now, so far, we're just looking at crests and troughs. We haven't looked at longitudinal standing waves just yet. Okay, let's now look at the different stages or the different phases in the cycle of a standing wave. So first, standing waves have cycles. They repeat. Standing waves have repeating cycles. Whoops, they have repeating cycles that repeat. Worth putting down. And we'll see that. So a standing wave starts out something like this. We'll do just one single wavelength. And after a little time, right, this particle has gone down, and this particle has gone up. And actually, after a little time, the standing wave makes a flat line. And then after a little more time, the standing wave is a mirror image of where it started. Right? These are mirror images. And then after a little more time passes, it's a flat line again. And if we wait just a little bit longer, we're back to where we began. Let me try that again. Back to where we began, something like this. So right here, and you know what, let's do, there's another standing wave that looks like this. You start with one big crest, and then it flattens out, and then it becomes a trough, and then it flattens out, and then we're back to where we started. That's another type of standing wave we'll encounter. At the very top, no time has passed. The amount of time that has passed is 0. Right here, how much time has passed? Well, it's been one full cycle, so that is equal to the period, capital T. This is halfway into the cycle, so half a period has elapsed. And of course then, this would be how much time has passed? A quarter of a period. Halfway between t over 2 and 0. And then, right here, how much time has passed? Well, it's halfway between capital T over 2 and capital T. So halfway between those two is 3t over 4. We could also write this as 0, but t is equal to 1 over f. So we could write this as 1 over 4f. And this we could write as 1 over 2f. And this would be 3 over 4f. And just 1 over f right here. So that's another way we can write these timing, the time frames. Oops, this was a 3. So let's see that in action. Here, from Wikipedia, is an image of lots of different standing waves we could produce. Each one is different from the others. And we imagine that this is a string that has been, we're vibrating the string up and down. Here, the string is like a jump rope, right? It's just going up and down. Here, we have we have a crest and a trough. Here we have 3 crests and troughs. Here we have 4, 5 crests and troughs, and then 6 here. So this is what we drew right here in this column. And this one is what we've drawn, that's this standing wave here. You see that the standing waves reach a point where it's a flat line, and then they just vibrate between being mirror images of themselves. Now we are going to take on the question, how are these standing waves produced? Well, let me give you just kind of a rough answer, and then we'll look at really the physics behind it. If you want to produce this standing wave right here, here's what you do. You take the string, you pull it down, and you let go. And you pluck the string, and it starts vibrating back and forth. In fact, when you pluck a guitar string, that's what you're doing. You're producing this standing wave right here that you see in the top left. Now, if you were for some reason being a little, if you were playing your guitar really oddly, you could take 2 fingers, put one here and the other at this spot, pull one finger up and the other down, and then let go, and you could maybe produce this standing wave, right, if you did it really well. So that's a kind of common sense explanation of how do you make a standing wave, but there's some underlying physics that we want to explore. To understand the underlying physics, I have a great simulation here that's going to help us see what's happening. To produce a standing wave, you need 2 traveling waves. They have to have the same frequency, wavelength, and same amplitude, and they must be going in opposite directions. If you have those 2 traveling waves, and you send them in opposite directions, they will interfere with each other to produce a standing wave. So here, the wave moving to the right is in blue. I'm going to hit go, and that one was going to move to the right. The green is moving to the left. And when you add together all of their displacements, it produces the red standing wave. So the standing wave in red is acquired by adding y1, the first wave, with y2, the second wave. Don't worry about these equations here. Let's watch the simulation. So cool. So see this blue crest moving to the right? We have a traveling wave, and a green crest moving to the left, where my cursor is, a traveling wave. They add together to produce this. Now, when the wave gets really high, whoops, let's try that again. When the standing wave gets really high, like right here, see how big the standing wave is? That's because we have crests overlapping with crests, right here, and troughs overlapping with troughs here, and then here crests overlapping with crests. There's perfect constructive interference at this location and at this location, and so forth. Right? Okay, now let's let the simulation run again, and I'm going to pause it when the standing wave, when the rope, is perfectly flat. Okay? And we'll see what's happening with the 2 traveling waves at that moment. Let's see how I do. Oh, I can do better than that. Not quite. There, perfect. At this moment, the rope, the thing that's vibrating, the medium, the rope, is perfectly flat. So what are the 2 traveling waves doing to produce this flat standing wave at this moment? Well, one wave is like this, and the other is exactly opposite, mirror images. So there's perfect destructive interference at this point right here. Perfect destructive interference at this point. Perfect destructive interference here, and all these other locations. We could like put a dot at the spots where there's perfect destructive interference. Right? So we see that there are certain locations where the waves have perfect destructive interference at a particular moment. And then there's other locations right here where a wave has perfect constructive interference. So constructive interference occurs here, and then the destructive interference will later occur like right here. See? Right here is the destructive interference, and over here was the constructive. Okay, back to the notes. We're going to come back to this just in a second, but I want to point something out. We saw on the next page of notes, there are places where we occasionally have complete or perfect destructive interference. There are other locations where we occasionally have perfect or complete constructive interference. Nodes is the term that we use for locations on a medium. Locations, let's say locations in a medium, that occasionally undergo perfect or complete destructive interference. Nodes, that's where we have destructive interference, causing the resultant displacement to be zero. Okay. And when we say perfect or complete, that means we have a trough on a crest. That's not very good. Perfect or complete means it's the very, very, very top of a trough with the very, 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 very bottom of a crest. So right here at this point, at this dot right here, the very tippy top of the crest and bottom of the trough are overlapping, so that makes it perfect, quote unquote, or complete. Antinodes or antinodes are the locations where two traveling waves occasionally undergo perfect or complete constructive interference. That means you have a crest on top. The tippy, tippy, tippy top of a crest is on the tippy, tippy, tippy top of another crest. So where are the tippy tops? Where are they meeting? They're meeting at this point on the rope, in the medium or on the rope. But not only could it be crest on crest, perfect constructive interference means it could also be trough on trough. But perfect means right at the middle, where the bottom of the two meet together. Right at that point where they meet. So now let's answer the question, how is a standing wave formed? The video helps us understand, but I'm going to tell you how we start making the standing wave at the very beginning. I'm going to consider, for this example, a pipe filled with air. Now, I'm not going to draw the air particles, but they're there. Now, what type of wave travels through air? So air is the medium in this example. What kind of wave goes through air? Sound waves, of course. So I'm going to create some sound waves using a speaker. Here's my speaker. It's making noise, making sound. The sound wave, I will draw it just here schematically as a squiggly line with an arrow showing where it's going. The sound wave is a continuous sound wave. So we create a continuous sound that keeps going from a source, the speaker, through a medium, air. That wave is sent through and it's reflected at the wall when it hits the edge of the air and it starts bouncing back. So the wave is reflected at the boundary, the wall. That's the edge of the air in the pipe. And then it goes back. But while this is happening, the wave is continuous. The sound keeps playing. The speaker keeps making noise. And so more waves are sent out while this first one goes down and bounces. So more waves are being sent. Here's my pipe again. Here's the speaker that keeps going. This one is reflecting back, but there's more coming its way. Like this, right? And what's going to happen? They are going to overlap. Or as we say, they will interfere. The incident waves, this is the incident wave because it's about to hit this one. The incident wave from the source interferes with the waves that are reflected. That's these.